Alright, this lecture is about solutions and the units we usually use to describe a solution, which is based on concentration. So first of all, let's define what a solution is. A solution consists of a solute, which is the substance being dissolved, and it usually translates also into the properties of the solution. And then we also have the solvent, and the solvent is the substance that does the dissolving. Most common solvent that we use is water. Now, how do we determine properties of the solution, like the amount of solute in the solution? Well, we use things like parts per million, parts per billion. We use percent concentration, and we use molarity. These are common solution or concentration units that we use to describe solutions. The most common in chemistry is molarity, but these other three are also important, especially in environmental science and biology, or also in consumer goods or consumer things that we would see in the newspaper. So parts per million, well, that means 1 over 1 times 10 to the 6, which is a million. So a part per million is 1 divided by 1 times 10 to the 6. A part per billion is 1 divided by 1 times 10 to the 9th. And then percent concentration is the amount of solute in the solution divided by the total amount of solute and solvent in the solute and solvent, which makes up the solution. Remember, when we talk about solution, we're talking about solute and solvent. All of that combined is the solution. Molarity, and this is generally in grams, or generally the solutes in grams, and the solute and solvent can either be in grams or sometimes it's in milliliters. Or both of these can be in milliliters, like the solute can be in milliliters and the solution can be in milliliters. So we would take this, multiply it by 100, and that would give us our percent solution. All right. So molarity is moles of solute per liter of solution. And the reason why chemists like this particular unit is because the moles translates very well into a balanced chemical equation where we have a certain number of moles of substance A reacts with a certain number of moles of substance B, and that forms a certain number of moles of substance C. Alright, now 1 part per million, we said it's 1 times 10 to the 6. Well, a good approximation of a part per million in water would be 1 gram of solute per 1 times 10 to the 6 grams of water, that being the solvent. Now again, this is a rough approximation because when we were really doing parts per million, we could well, let's forget that for this moment. Okay, so 1 part per million is 1 gram of solute per 1 times 10 to the 6 grams of water. Now, we can change the grams of solute. 1 gram of solute is equal to 1,000 milligrams of solute. All we're doing here is changing our units from grams to milligrams. So 1 part per million can be thought of as 1 gram per million grams of water, or 1,000 milligrams per million grams of water. Now, if we want to change this to a volume, we're going to approximate that the density of water, and I'll put that here, the density of water is 1 gram per milliliter. Now that's an approximation. The only time it really comes close to that number is at about 4 degrees Celsius. But this is an approximation that we use quite often in chemistry, that the density of water is equal to 1 gram per milliliter. So we've got 1,000,000 grams of water, and we know that 1,000 grams then of water would equal 1 liter. And you say, how did you get that? Well, if 1 gram of water, the density of water is 1 gram per milliliter, and I have 1,000 grams of water, then I would have 1,000 milliliters of water. And let me just write that again, because I think this is where the confusion is. 1 gram of water occupies a volume of 1 milliliter. All right? So 1,000 grams of water would occupy a volume of 1,000 milliliters. And again, this is an approximation, but it's a pretty good one. And so we could also say this: 1,000 grams of water is equal to 1 liter of water, because 1,000 milliliters is equal to 1 liter. Remember when we did the conversions, 1 liter is 10 to the third milliliters, or the way we did it in class was 1 milliliter is equal to 10 to the negative third liters. All right. So another way to think of it is, as a milliliter is 1/10 or 1,000th of a liter of water. So you got to have 1,000 milliliters to equal 1 liter of water, and 1,000 milliliters of water approximately weighs 1,000 grams. So here what we're doing is converting from grams of water. This is in the denominator up here. This cancels with the numerator. And so what we end up with then is when we take the 1,000 here and the 1,000 here, and we divide it by 1 times 10 to the 6 here, we get that 1 milligram of solute per 1 liter of water is approximately equal to 1 part per million. So that's just an approximation, that when somebody says there's 1 part per million mercury in the water, that would be saying there's about 1 milligram of mercury per liter of water. All right. Part per billion, again, 1 times 10, 1 gram of solute per 1 times 10 to the 9th grams of solvent, or in this case, water. All right, so what do you do with these things? Well, you can do conversion factors. If somebody says that I have 5.3 moles of sodium chloride, and I dissolve that in 5,000 milliliters of solution, what is the molarity? What is the molarity of the solution? So the definition of molarity is a capital M equals, sometimes underlined to emphasize that it's capital. Capital M equals moles divided by liters, and we have 5.3 moles of sodium chloride, and we're dividing that by 5,000 milliliters. Well, we need to convert that to liters, so 5,000 milliliters, and we know that 1 milliliter is 10 to the negative third liters. So 1 milliliter, 10 to the negative third liters. So 5,000 times 1 exponential negative 3 would give us 5 liters. So if I take 5.3 moles of sodium chloride and I divide it by 5 liters of solution, that will give me the molarity of the sodium chloride in this solution. So take 5.3 divided by 5, it equals, and we get 1.06, but because we only have one significant figure in this number here, my answer would be 1 mole per liter. And then you always write what it's of, sodium chloride. Or you could write this as 1 capital M NaCl. You can do it that way too. So you may be going, well, what good is that? What do I need to know that? Well, if somebody says I have 45 milliliters of 1 molar NaCl, you can tell me how many moles of NaCl you have. How many moles of NaCl that you have. You go, well, how do you do that? Well, the 45 milliliters, you need to convert that to liters first. So that'd be 45. Here's the fast way to do this. 45 milliliters means 45 times 10 to the negative third liters. Milli means 10 to the negative third. And if I multiply that by the concentration of 1 mole per liter, the liters will cancel out here, and I'll be left with moles of sodium chloride. So take 45 exponential negative 3, 45 exponential negative 3, and we multiply that by 1, and we get 4.5 times 10 to the negative 2 molar, or not molar, oops, wrong. 4.5 times 10 to the negative 2 moles of NaCl. All right. So when we know concentration, we can take volume. We know how much solution we have and what the concentration of the solution is. We can determine how many moles of the solutes in that amount of solution. So that's an important ability to be able to tell me how many moles of a particular solutes in a solution, because it is those moles that react with other substances in a balanced chemical equation to form a certain number of moles of product. I hope this helps, and I can do more if you request it. Thanks.